Hello students, today we are going to study nitrosoureas. This is the second class of alkylating agents of the category anti-cancer drugs. These drugs are very important. Nitrosoureas are unstable in aqueous solutions and under physiological conditions. They produce alkylating agents which then alkylate DNA and prevent their replication. So the nitrosoureas namely are carmustine, lomustine, and streptazosine. The general structure of nitrosoureas is urea, so it has the structure of urea. Then it is nitrosourea, so nitroso group is attached. Then we are going to study the first structure, that is carmustine. So it is the structure of carmustine is there is ethyl chloride group to one end of the nitrogen, and the same structure is here also, that is ethyl chloride to other end. This is the structure of carmustine. Lomustine also is a nitrosourea, so it has the same structure. This is nitroso group attached here. To one side there is ethyl chloride, and to other end we have a cyclohexane group. So this is the structure of lomustine. Then the next nitrosourea is streptazosine. The structure is similar, the nitrosourea part is similar. So we will draw here double bond O, then it is NH. To this side we have a pyranose ring. CH2OH, here OH, hydroxy group. So there is a glucopyranose ring at one side of the nitrosourea, and to the other side we have methyl groups. So these are the three structures of nitrosourea groups. Now all these drugs three drugs, carmustine, lomustine, streptazosine, they metabolize first and generate carbonium ion that can alkylate our DNA, and isocyanate ion that can carbomylate. So that is the mechanism of action. So we'll see the mechanism of action of nitrosoureas. Now we will see the mechanism of action and metabolism of Nitrosoureas. So we have here with us one Nitrosourea, a general structure of a Nitrosourea class of drug. There is hydrogen, then the other group is R. This structure undergoes deprotonation reaction, so I will write down here minus of H plus. This proton is released from the nitrogen. Once it is released, it leaves the lone pair of electrons on the nitrogen. So we have with us another structure, that is chlorine. We have nitrogen and nitro group, C double bond O, then nitrogen with the left lone pair of electrons. In the next step, the lone pair of electrons move here. They are very unstable and they try to move here to form a double bond, and which makes this carbon unstable and the oxygen pull towards itself the pair of electrons. So what happens? There is the next step we can see here. There is chlorine, a nitrogen of nitro group. We have C with O minus and a double bond N and R. Now what happens? Now there is a formation of isocyanate. So if you observe the structure, this part RNCO, this is the structure of isocyanate. So this structure, this oxygen, it is unstable. It gives the electrons towards the carbon, then the carbon becomes unstable again. So there is a breakdown of this bond, which forms a double bond with among this two nitrogen, and we get our isocyanate. So we have the structure R, N, double bond C, double bond O. This one is isocyanate. The carbon here reacts with the lysine amino group to form the structure lysine NH, C double bond O, N, R. This is carbomoylated lysine. This is the fate of isocyanate. Then here a proton adds up and we get the structure chlorine. There is a structure of hydroxide N, double bond N with OH. This is hydroxide. In the next step, there is a cleavage of this bond. So here then generates a chloroethyl carbocation, then N2 with the liberation of a nucleophile. This chloroethyl cation now attacks, this is a alkyl group or a electrophile generated by Nitrosourea. Now it is ready to attack our N7 position of guanine in DNA. So we have the next structure, that is CH2. This way one of the strand of DNA is damaged. I will write G for guanine and DNA. The chlorine is highly electronegative. It will leave the group since it is a very good leaving group also. Then again there is a charge developed on this particular carbon, which is a positive charge, CH2, G and DNA. Next what happens, again this electrophile is now ready to attack the N7 position of guanine in DNA. So we have CH2, G, DNA and G, DNA. So this is the alkylated DNA with the nitrosourea. This way the DNA is alkylated with the help of nitrosoureas. Soon we will see the next pathway, the other pathway. Now we will see second pathway of nitrosoureas. So for that we need a structure of nitrosourea. Here we have chlorine, nitrogen attached to the nitroso group. We have C double bond O, the urea, and this is R. So this is the second pathway. Like in the first pathway, the second pathway also starts with deprotonation. So I'll write down minus of H plus. Deprotonation leaves 2 electrons on nitrogen. So it is C double bond O. We have N and R. In the next step, the electrons move here. Oxygen pulls electrons to make this carbon stable, and we have the next structure, that is chlorine with hydrogen, double bond O. Then we have C, O with a negative charge, C double bond N and R. Now this step varies from the first pathway in a manner that there is a formation of oxazolidine ring in the structure. Now how that oxazolidine ring is formed? The chlorine here is a good leaving group, so it leaves, okay, giving a slight positive charge to this carbon. Now this plus and this minus forms a bond and undergoes cyclization. So there is a formation of a cyclic structure. We'll form the cyclic structure. We have a nitrogen with a double bond, then we have one more nitrogen here. There is carbon which is attached to the double bond N, and there is R here, oxygen. Oxygen is now attacking this plus charge, so we have one carbon here. There is another carbon, this carbon here, which is attached to the nitrogen. So this way the oxazolidine ring is formed. Now again we know that there is a formation of isocyanate. Now to form isocyanate, we can see the structure right from here, RNCO. So there will be a breakdown to form this isocyanate. So naturally the bond will break from here and from here to give double bond O, double bond C, double bond N and R. So this is isocyanate, which either goes for carbomylation or in the presence of water it releases CO2, forming a primary amine. The isocyanate which is formed from this structure now uses a water molecule to form CO2 and a primary amine. Now we'll see what is left with the structure. The left part is, here it is CH2, there is CH2, then there is N, N and O. We just have to adjust the bonds. So this bond will move here to form a double bond. So we have with us CH2, double bond CH, then which is bonded to the nitrogen. Every time you should balance the valencies, then N, which is bonded to the double bond nitrogen, and double bond O. I'm sorry, here it will be OH. So there will be OH. There will be a breakdown here to form acetaldehyde, CH3, C, double bond O and H with the release of nitrogen, or it will lead, the same breakdown may lead to the formation of CH double bond CH2 vinyl carbocation. Vinyl carbocation. Now this vinyl carbocation, the acetaldehyde, the isocyanate generated, these are very important metabolites of nitrosoureas. This vinyl carbocation is now ready to alkylate our DNA, and it also there is also the liberation of N2 with the liberation of a nucleophile. So that's all. This is the second pathway. wherein the nitrosourea loses the proton, then forms a oxazolidine ring, which then leads to the formation of isocyanate, further forming vinyl carbocation, which is now ready to alkylate the DNA. This way, this is the mechanism of action of nitrosoureas. Thank you for watching. If you like my video, please share and subscribe. Thank you.